A graph neural network is not a sequence model bent onto a graph, nor an image model with irregular pixels. It is a parametric function defined directly on a graph, a rule that transforms features attached to nodes by repeated local computation over neighborhoods, and that is constrained, before any weights are learned, by a single symmetry. Relabeling the nodes must not change what the function computes. From that one primitive, read the neighbors, combine them, update the node, every architecture in this field is assembled. This film develops that object formally, its domain, its symmetry, the message passing layer, the standard architectures as instances of one operator, and the exact limits of what such a network can tell apart. Begin with the domain. A graph is a set of vertices and a set of edges. Its structure is recorded in an adjacency matrix A, an n-by-n array whose entries mark which pairs of nodes are connected. Onto this structure we place a signal. Every node V carries a feature vector, a point in d-dimensional space, and stacking these gives a node feature matrix X with n rows and d columns. Edges may carry their own features as well. A graph neural network operates on the pair, the structure A and the signal X, and returns a new signal of the same shape. The running specimen fixes this once: 6 nodes, a chosen target node V, and a short feature column drawn beneath each node. A graph neural network presupposes its input. 2 things must be supplied before a single message is passed: a graph and a vector on every node, and neither is always given. When the data is not natively relational, the graph itself is a modeling choice. Nodes are joined by a rule, a nearest neighbor rule on some similarity, a domain relation, a threshold on a distance. That constructed structure bounds everything the network can later propagate. The node vectors are the initial representations, the layer 0 states. Where attributes exist, text, images, categorical fields, an encoder maps them into a shared d-dimensional space. Where a node carries no attributes at all, the network learns an embedding for it directly, a trainable vector per node. Structure and features are not incidental decoration. They are the substrate that message passing runs on, and no aggregation can recover information the graph and its embeddings never encoded. Why not simply reuse the machinery of grids and sequences? Because a graph has no canonical geometry. Neighborhoods differ in size. One node has a single neighbor, another has 3. There is no natural left or right, no shared coordinate system, no translation that carries one neighborhood onto another. A sequence and an image are only special graphs, a chain and a lattice, in which every neighborhood looks identical, which is exactly what lets a convolution slide a fixed stencil across them. On a general graph, that fixed stencil does not exist. The operation that replaces it must accept a neighborhood of any size and must not depend on the order in which the neighbors happen to be listed. That requirement is a symmetry, and it is the design prior of the entire field. Let P be a permutation matrix that relabels the nodes. Relabeling acts on the signal as X maps to PX, and on the structure as a maps to PAP transpose. A function that produces one vector per node must be permutation-equivariant, computing on the relabeled graph, f of px and PAP transpose, must equal p applied to f of x and a. The outputs are simply carried along by the same relabeling. A function that produces a single vector for the whole graph must be permutation-invariant. The relabeling leaves it unchanged. This symmetry does not describe a network after the fact, it selects, in advance, which layers are admissible at all. Locality supplies the rest. The neighborhood of a node V is the set of nodes joined to it by an edge. A single layer updates each node using only its own state and the states of its immediate neighbors. Nothing further away is consulted in one step. Stack the layers and reach extends by exactly 1 hop per layer. After 2 layers, a node has been influenced by everything within 2 edges, after L layers by its entire L-hop neighborhood. The computation seen from one node is therefore a tree: the node, then its neighbors, then their neighbors, the unrolled receptive field. In the specimen, the target node first reads nodes 2, 3, and 4. A second layer pulls in the nodes behind them. The local step has 3 parts, and the first is the message. Along every edge from a neighbor U into the target V, the network computes a message, a learnable function psi of the neighbor's state, the target state, and any feature on the edge between them. Written out, M from U to V equals psi of HU, HV, and EUV. The function psi is typically a small multilayer perceptron shared across all edges, so the same rule is applied everywhere. Each edge thus produces its own vector, a tailored contribution that node U sends to node V. Nothing has yet been combined. There is one message per incoming edge, computed independently. The messages must now become one vector, and here the symmetry returns as a hard constraint. The aggregate of node V is a combination, over all neighbors U in the neighborhood, of the incoming messages, written with a general aggregation operator. That operator must be a function of a multiset, a collection with repetition but no order, because the neighbors have no order to respect. Summation, averaging, and element-wise maximum all qualify. Each ignores the sequence in which the messages arrive. This is precisely where permutation-invariance is discharged inside the layer. The choice is not cosmetic. Summation preserves the most information about the multiset, while averaging and maximum deliberately discard some, and that difference will decide how much the network can tell apart. The third part closes the layer. The update function phi takes the node's current state together with the aggregated message and returns the node's next state. HV at layer L plus 1 equals phi of HV at layer L and the aggregate. The node keeps a channel to its own past state, so information is refined rather than overwritten. These 3 steps, message by psi, aggregate by the invariant operator, update by phi, are the entire message passing layer, the primitive introduced by Gilmer and colleagues. Every graph neural network in common use is one specific choice of these 3 functions. The remainder of this film is a tour of those choices, drawn on the same graph. The same layer has a second face. Written for all nodes at once, a message-passing layer of the summation or averaging kind is a matrix expression. The next feature, matrix H prime, equals a nonlinearity sigma applied to A hat times H times W. Here H is the current signal, W is a learnable weight matrix mixing feature channels, and A hat is a normalized adjacency operator that routes each node's features to its neighbors. Message passing is thus a sparse matrix multiplication followed by a pointwise nonlinearity, and the sparsity of A hat is exactly the locality of the primitive. A zero entry is a missing edge, a message that is never sent. The per-node view and the matrix view are the same operator, read node by node or all at once. Depth in a graph network means reach, not merely capacity. Because one layer moves information a single hop, the number of layers sets the radius of the receptive field. A node can only be affected by another node if the two are within as many edges as there are layers. Seen from the target, each added layer wraps one more ring of the graph into its unrolled computation tree. This has a consequence for design that has no analog in a fixed grid. If a task depends on a relationship spanning 6 hops, a network of 3 layers cannot represent it at all. The relevant node never enters the computation. Too little depth underreaches. As we will see, too much depth brings a failure of its own. The first standard instance is the graph convolutional network. It collapses the three functions into their simplest useful form. The message is just the neighbor's transformed features, and the aggregation is a symmetrically normalized sum. Its operator a hat equals d tilde to the -1/2 times the adjacency with self-loops added times d tilde to the -1/2, where d tilde is the degree matrix of that self-looped graph. Each edge is therefore weighted by 1 over the square root of the two endpoint degrees, damping the influence of high-degree hubs. A single layer reads h prime equals sigma of a hat hw. This operator is a first-order localization of spectral graph convolution, reduced to a rule that touches only immediate neighbors. GraphSAGE keeps the self-state and the neighborhood explicitly separate. Its update concatenates the node's own vector with an aggregate of its neighbors, then applies a weight matrix and a nonlinearity. HV prime equals sigma of W applied to the concatenation of HV and the aggregated neighbor states. Two design choices follow. First, because self and neighbors occupy distinct slots, the node never loses its own identity to the average. Second, the neighborhood is sampled to a fixed size rather than read in full, which bounds computation on large graphs. Crucially, GraphSAGE is inductive, since the learned functions depend on features and local structure, not on fixed node identities. A trained model applies to nodes and even whole graphs never seen during training. The graph attention network makes the aggregation weights themselves learned and data-dependent. For each edge, it computes an attention coefficient alpha UV, a score formed from the two endpoint states, then normalized by a softmax across all neighbors of V so the incoming weights sum to 1. Aggregation becomes a weighted sum. Neighbors judged more relevant contribute more. Unlike the graph convolutional network, whose weights are fixed by the degrees, attention lets the network decide, per edge and from the content, how much each neighbor matters, so the operator is anisotropic. Several attention heads are usually run in parallel and combined, giving the layer multiple independent notions of relevance over the same neighborhood. The graph isomorphism network is the instance built for discriminative power. Its aggregation is a plane sum, and its update is a multilayer perceptron applied to the node's own state, scaled by 1 plus a parameter epsilon, added to the sum of the neighbor states. The reason for these exact choices is that a sum over a multiset, followed by a sufficiently expressive perceptron, can be made injective distinct multisets of neighbor features mapped to distinct outputs. Averaging and element-wise maximum cannot. A neighborhood of one blue node and a neighborhood of two blue nodes have the same average and the same maximum, and are thereby merged. By preserving the multiset, this network reaches the maximum distinguishing power available to any message-passing scheme. So far, every layer returns a signal, one vector per node, which already serves node-level tasks such as classification and edge-level tasks such as predicting a missing link from its two endpoints. A graph-level task needs one more step, a readout that collapses all node states into a single vector for the whole graph. That readout must itself be permutation-invariant, since the graph has no preferred node order. A sum, an average, or a maximum over all nodes qualifies, as do more expressive invariant pooling schemes. The pattern is uniform. Message-passing layers produce equivariant node representations, and an invariant readout converts them, when required, into one representation of the entire graph. How much can such a network distinguish? There is an exact ceiling. Message passing can tell two nodes or two graphs apart only as well as the one-dimensional Weisfeiler-Leman test, a classical procedure that repeatedly recolors each node by hashing the multiset of its neighbors' colors. Any message-passing network is, at best, a learnable version of that refinement. The consequence is sharp. If the test assigns two non-isomorphic graphs identical colorings, then no such network, at any depth and for any parameters, can produce different outputs for them. Two regular graphs, a single six-cycle and two disjoint triangles, are the standard witness. Every node always sees two neighbors just like itself. The colors never separate, and the graphs are invisibly identical to the network. Summation aggregation attains this ceiling, averaging and maximum fall below it. Depth, which we praised as reach, carries the opposite danger. Each aggregation is a form of local averaging, and local averaging is a low-pass filter. It smooths differences between neighbors. Apply it many times and the node representations contract toward one another, in the limit toward a single vector fixed by the graph's degrees, independent of the input features. This is oversmoothing. Beyond a moderate number of layers, the nodes become nearly indistinguishable, and the discriminative content the network was built to produce decays away. It is the precise tension at the center of graph learning. Reach demands depth, but naive depth erases the very distinctions it was meant to gather. A second limit is topological. The receptive field of a node grows exponentially with depth. A few hops can already encompass most of the graph, yet all of that information must be compressed into a fixed-width vector. When many paths funnel through a narrow region of the graph, a bottleneck, the messages crossing it are squashed together, and the distinct signals they carried are lost. This is oversquashing, and it is why long-range dependencies are hard for message passing to preserve even when the depth is sufficient to reach them. It is a different failure from oversmoothing. Oversmoothing erases differences by repetition. Oversquashing erases them by compression through the structure of the graph itself. The learning procedure adds nothing exotic. A loss is attached to whatever the task requires, a label at each node, a score on each candidate edge, a target for the whole graph, and gradients are propagated back through the unrolled message passing by ordinary backpropagation, exactly as in any other differentiable model. Two regimes are worth naming. In the transductive setting, the graph is fixed and only some node labels are known, so training and prediction happen on the same structure. In the inductive setting, the model must generalize to graphs unseen during training, which is possible precisely because the learned functions act on features and local structure rather than on node identities. The inductive bias lives in the operator, not in the optimizer. The graph neural network is now fully specified as a formal object. Its domain is a graph carrying a signal on the nodes. Its governing prior is permutation symmetry, equivariant node maps, invariant graph maps. Its primitive is a single local layer. Compute a message on each edge, aggregate the neighbors with an order-independent operator, update the node. That primitive has a matrix face, a sparse normalized multiplication, a depth, which is reach, and a family of instances, convolutional, sampled, attentional, and injective, that differ only in the three functions they choose. An invariant readout lifts nodes to graphs. And its limits are known exactly, the Weisfeiler-Leman ceiling on what it can distinguish, oversmoothing with depth, and oversquashing through bottlenecks. Define the domain, respect the symmetry, choose the primitive, and read its consequences. Neural Cipher. Deciphering learned computation.